complexity of slab design, how the slab actually is designed. So first we have to know what is slab. So let's start. So introduction of slab. What is slab? What is actual slab? The slab is a flat horizontal structural element used in construction to create floor, ceiling, roofs. So it is an horizontal structural member which is used in construction to create floor, ceiling, and roof. So there are two types of slab in construction. There is a one-way slab and there is two-way slab. So first we will check for one-way slab. सर वो नीचे नहीं हो रहा है इसमें. हेलो हेलो.
हेलो.
हाँ सर आवाज आ रहा है.
यस यस परफेक्ट.
सर वो नीचे नहीं हो रहा, मतलब स्लाइड चेंज नहीं हो रहा.
ओहो. एक बार स्केप दबाओ, स्केप दबाओ.
उसके भी नहीं दब रहा.
राइट क्लिक करना.
नहीं
राइट
सर नहीं.
यहाँ पर देखो नेक्स्ट तो हो जाएगा बट नेक्स्ट करना समझदारी नहीं है. इसको इंड शो करो, इंड शो, लास्ट लास्ट ऑप्शन. हाँ यहाँ पर उसी जस्ट पहले एक रीड व्यू है, रीड व्यू कर दो. जहाँ पर क्लिक करके फुल स्क्रीन किए थे नीचे 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 उसके जस्ट पहले रीड व्यू है. हाँ इसके जस्ट आगे वाला ये कर दो. परफेक्ट.
Yes. So there are two types of slab in construction: one-way slab and two-way slab. So first we will check what is one-way slab. So guys, one-way slab is a type of concrete slab that is designed to carry load in one direction. One-way slab transfer load in two supporting beams. So there is a formula for calculating one-way slab, that is Ly by Lx, which is greater than 2. We will consider as one-way slab. As you see in the figure, there is an this diagram is for one-way slab. Uh, so for two-way slab, what is two-way slab? A two-way slab is a type of slab that is designed to carry load in two directions. Two-way slab transfer load on all sides, all four sides, all supporting beams. So there is a formula for calculating two-way slab, which is Ly by Lx is less than 2. We will consider as two-way slab. There is an intent mistake in this. We will consider this a two-way slab. This is the this is drawing. This is a drawing of two-way slab where all the sides are carried by uh, supporting beams. So how so today we will learn about how we will calculate one-way slab manually. So there is an example design of simply supported roof slab for a room of 7 by 7.5 into 3.5 clear size. The slab is carried an imposed load of 5 kilonewton meter square. So use M20 mix and Fe 400 steel. So there is a room of clear span which is 7.5 into 3.5. 7.5 is a longer span and 3.5 is a shorter span. And the imposed load is given in the as given in the question, 5 kilonewton per meter square, and we use M20 grade of concrete, and still we will use Fe415 still. So let's start our design. So first solution. So first we have to check this is one-way slab or two-way slab. For checking this, there is a formula Lx by Ly by Lx. So Ly is a longer span and Lx is equal to shorter span. So the value come is 2.4, which is greater than 2. So the value is greater than 2. So it will be considered as one-way slab. Next. So first step to calculate one-way slab. So we have to first calculate total depth and effective depth. So as per thumb rule, there is a formula D equals to L upon 25. So D is our 3.3 3.5 m meter. So convert into mm. It will be 3500 uh, divided by 25 equals to 140. So total depth we get 140 mm. As clear cover, we will take 20 as per 456 2000 clause 26.4.2, or we will refer to table number 16. So we will consider a dia of 10 Assume we are taking 10 So effective depth equals to, the formula is total depth to get effective depth. There is a formula, total depth minus clear cover minus radius of the bar. So clear cover we will have 10 d minus 20, and the radius of the bar half of the bar. So 10 upon 2. So effective depth will be, we will get 125. So this is the effective depth. The step 2, effective depth L. Clear to get effective depth, there is a formula. L is equal to clear span plus effective depth as per clause 22.2 or page number 34. So L, putting value in this, L equals to 3.5 plus 0.125, which is effective depth we get in last slide. L equals to 3.625. So effective span we will get. So you have a question, why we taken L equals to 3.5 instead of 7.5? Why we not taken 7.5? So as per IS code note, in one way slab we have to take only shorter span, but in two-way slab we consider both longer span and shorter span. But in one-way slab we have to always take shorter span for designing. So for the step 3, so we will now calculate design load, which is W, factor moment Mu. So calculating design load, we have to first need total load. So first we will calculate self weight of the structure, which is called as dead load. Which is also called as dead load. Dead load is equal to D, capital D into B into unit weight of the RCC. So 0. Putting value in this 0.15. We have to always consider as assume as 1000. So we will consider 1000 is equal to 1. So into 25 we will get unit weight of RCC, as you know, which is given in clause number 19.2 or page number 32. So DL equals to 3.750. Now we have to calculate live load also. So live load is already mentioned in the given example. So which is 5 kilonewton per meter square. So LL is equal to 5 into B, which is B equals to, as we already say, I said we have to assume B equals to 1000 always. So B into 5 into B equals to 5 into 1. So which will LL equals to 5 kilonewton per meter. So next. So after that, after getting self weight and live load, after this we have to calculate total load which is coming to the structure. So DL plus LL, putting value in this 3.750 plus 5. So total load we will get 8.750. So now we have to calculate design load. So what is the formula of design load? Design load into factor of safety. So design load equals to factor of design load we get 8.750. So this factor of safety, this is mentioned in the clause number 18.2.3.1 or page number, I forgot to type. So 18.2.1, there is a specific note for this factor of safety. So for from there we will take 1.5. So design load equals to W equals to 13.125 kilonewton after calculating this. So after calculating design load, we have to calculate factor load also, factor moment. So for factor moment, there is a formula: design load into effective depth upon 8. which is WL square upon 8. The fact mu will we get 21 kilonewton per meter, or in terms of Newton mm, 21.6 into 10 raised to 6 Newton mm. So after calculating this, we will go to the next slide. The first step is for calculating effective depth required. Effective which effective depth, how many effective depth required for the structure. So take XU max upon D value for 415, which is mentioned in table number 70. There is a table at page number 70. So XU max value for 415 is 0.28, which will be mentioned in IS code as per table number 70. Page number 70, there is a table. So we have to calculate effective depth. So there is a formula for MU limit in Annex G, clause number 13.1. So what is the formula for it? MU equals to 0.36 XU max upon D, which is this, 1 minus 0.42 XU max upon D into BD square FCK. So putting value in this equation, in this formula, this is the values we put in this. So after putting this value, we will get D required, which is 0.18. So D required 0.18 is less than 125, which is already calculated in the second step, effective depth 125. So this value which is required, and our value is greater than this. So hence the it is safe and okay. After calculating this, we need to calculate the area of tensile reinforcement. To calculate area of tensile reinforcement, there is one formula. Mu equals to 0.87 Fy D 1 minus AST upon Fy upon BD FCK as per clause 38.1. So put all the respective values in this formula. After putting these respective values, we will get AST equals to 523 upon 4, 523.4 mm square. So now we have to calculate spacing between steel at shorter span. First we will calculate for the shorter span. So we assume 10 mm dia bars. So area, we have to calculate area of one bar. So area of one bar formula is pi upon 4 d square. So pi value will get d is equal to 10 square. So value we will get 78.5 mm square. After this, spacing of 10 dia bars equals to uh, for this is the value of one bar. So for all the bars, we will there is a formula B into A dia upon AST. So after putting these values, we will get 150.17 mm. So provide 10 mm dia bar of bars at 150 center to center distance. So we will, from this we will get shorter span. So now we have to check this spacing is right or wrong. So we have to check this. For checking this, there is a clause 26.3.3 B section, or you can refer page number 46, where they are mentioned. The spacing should be less than 3D, which is 3 into 125 effective depth, which we will get 375, or the second term is given in the IS code. It should be less than 300. So effective depth we get 150, as you know, 150 we will get. So which is less than 300. Second term, it should be less than 300 or 375. So 300 is less than 375. So this value is also smaller than this value, 150. So hence is okay. So this is for shorter span. Now we will calculate for longer span. So step is for distribution of steel in a longer span. So take 0.5 of cross sectional area. This is a formula for distribution of steel in to calculate distribution of steel in larger span. take 0.15 of cross section, which is this formula is from clause number 26.5.2.1, or you can also refer the page number 48. So putting this value 0.15 upon 100 into B, which is 1000, and the effective depth equals to, we will get the value 225 mm square. So now assume, as you assume 10 mm dia for shorter span, as we assume now we assume 8 mm dia bars for longer span. So first we have to calculate for one area of one bar. So after calculating, putting this formula, area of one bar equals to 50.24. So spacing equals to B into A dia upon AST. For we have to calculate for longer span. So 1000 into this value, area of one bar into 125, which we get in this. So spacing equals to, spacing value will be given 223 mm, which is also equals to 230. We will take larger 230 mm. So now we have to check shear. Factor SF factor SF VU is equal to what is formula for checking the shear? VU is equal to dead load into clear span upon 2. So W into L square upon 2. So after putting this all values, we will get 130 point, in this we will get VU is equal to 22.97 kilonewton, or 22970 Newton. So now we have to calculate nominal shear TU. So TU is equals to VU on V upon D. This for nominal shear stress, there is a formula at page number 73 or clause 40.1. So after putting these values in this formula, we will get TU, tau V. So 0.18 Newton mm square we will get. After that, uh, we have to calculate design shear strength for concrete. So now we have to calculate design shear strength of concrete, which is tau C. So percentage of steel, how to calculate it? Percentage of steel is equal to 100 into AST upon 2 upon BD. As per clause 40.2.1, there is a table in it. So these are the clauses are in this on that table number 19. So percentage equals to 100 into 523 upon 2 upon 100 into 125. Put all the values in this formula. We will get percentage of steel, which is equals to 0.25. So now refer the table where all the values are coming. So our value, there is a table where all the values are given for M10, M20, M30. So our value is coming in between 0.115 to 0.25. So now we have to calculate this tau C equals to 0.25 plus 0.36 minus 0.28 upon 0.25 minus 0.15 into 0.21. So this all values are between 0.1 to 0.5. So we have to refer this table number 19 to calculate this. So 0.21 minus 0.15, the tau C we will get 0.328 Newton per m square. So note. So now check the tau C is greater than tau V. So tau C, what is the value of tau C? Tau C is 0.18. Tau V equals to 0.18, which is less than 0. Tau, which is less than 0.328. So tau C is greater than tau V. So hence, okay. So now we have to check for deflection. Check for deflection, the formula is check for deflection is percentage of steel equals to 100 into AST upon BD. So what is take this 100 into what is the value of AST? We have got 523 upon this is 1,000, but by mistake it is print 100 into what is D we get 125 into we have to calculate percentage. So multiply it by 100. So percentage of steel we will get 0.4 percentage. Now we have to calculate the uh, steel stress of service. Steel stress of service, how we will calculate Fs, there is a formula for it. Fs equals to 0.58 Fy. AST require still required and AST still provided. So as per table of modification factor, page number, this formula we will get in page number 38. There is a modification table. So putting all values in given formula, so we will get 240 Newton per mm square. So now check percentage of steel and Fs in figure number 4 and page number 38. So there is a table uh, in between. We have to check uh, there is a Fs value which is where the values lies in that table. So as per Fs value of percentage of steel lies in between. So our values lies in between 1.5 or 1.55. So modification factor we will take 1.55. Refer the figure number 4 at page number 38. So now check L upon D max is greater than L by D provided or not. So now check effective depth ratio as per clause 23.2.1 section A. So there are the values of the depth ratios are mentioned. For cantilever it will be 7, for simply supported it will be 20, for continuous beam we will take 26. But now our equation our design is design and the question in which they are mentioned, this is for simply supported. So we will take simply supported value. L upon D max equals to 20 into 1.5. So this value we will put, and this is we get modification factor. So effective depth ratio into modification factor we will get 31, and what it will be, what we provided, L upon D provided equals to effective span upon D. So effective span we get it 3.625, convert into mm we will get 3625 upon 125. The value equals to 29. So LD max is greater than LD provided, L by D provided. So hence it will be okay and it will be safe structure to design. So step 9, this is the last step for this uh, design. Check for the development. Now here we have to calculate development. So first calculate moment of resistance at support by 10 mm dia at 300. So M1 equals to this is there is a formula for calculating moment of resistance. So there is a formula M1 equals to 0.87 Fy dot into ASTD in bracket 1 minus Fy AST upon FCK upon BD. This formula we will get in as per clause 38.1 to check the moment of the resistance at support. So now put all the values in given formula. We will get M1. M1 we will get M of 11.47 into 10 raised to 6. And we already get VU is equal to 22.970 Newton. This value is getting in the last steps. So now we have to assume we not provided the hooks. In bending development length, there is are hooks to join it. So we have to assume it there are we don't provided hooks. So L0 LO is equal to 0. So as per 26.2.3.3, there is a value for L0. So there is no hooks, we will take 0. So there is a formula uh, uh, as per clause 26.2.3.3 N1 upon V plus L0. So putting these values, all values in this, we will get 11 point. By putting this value, all values in this, we will get 499.23, which is equals to 500. So now we have to calculate the development length. What is the formula for development length? LD equals to 0.87 Fy uh, dia upon 4 tau BD. So putting all the respected values in this equation, we will get development length, which is LD equals to 470 mm. So we will get development LD, we will get this. So M1 upon V plus L1, which is this value, is greater than this value, which is get. So hence hence okay, the structure is safe. So now we will see how the diagram will be done. So the values of 10 mm dia at spacing 150 center to center, which is we calculated for shorter span. So these are the bars which are gone in shorter span. So there is this dia will be 10 mm of 10 mm at spacing 1 150, which is for shorter span, and for longer span we take 8 mm dia as you seen in last steps. So the value which we got 230 mm center to center for longer span. So this 10 mm at the rate 300 cc is for the distribution bars we get value getted in the last steps, and this is the span, shorter span from here to here, as mentioned in the question 3.5. This is the shortest path. This is for shortest. So this is how we will design one-way slab in the respective scenarios. So thank you guys. I hope you understand, and thanks to sir to giving me this opportunity to present my PPT.
ग्रेट, बहुत ही सुंदर, बहुत ही डेप्थ में बताया ना, बहुत ही आराम से, मतलब एकदम इजी लैंग्वेज में था गाइस, कोई भी समझ सकता था। बहुत सुंदर, थैंक यू सो मच रत्नेश, मजा आया। तुमको भी अच्छा लगा होगा कि प्रेजेंटेशन से हमारी कॉन्फिडेंस
Yes.
रेज हुआ, है ना?